jet substructure techniques which we use in our field. Now, I'm going to take a step back and kind of try to motivate how we use these things in experiments. Okay. Okay, thanks. And what are the things we can do? In the last 5 minutes of Deepak's talk, I was desperately trying to find a picture of Florida beating Michigan State, but I couldn't find a recent one. I needed a bit more time. we are doing terribly this year, getters sir, but we had our day. Anyway, right. So I'm not going to spend any time on these things, except perhaps saying why jet substructure is important, especially for us, because in busy final state, for example, this is like a W prime decaying in hadronic channel where you have 2 jets and 2 B jets, or the famous TTH to BB, where you can have both tops decaying hadronically. Then you have, 4 B jets and 6 B jets and 4 light jets. So we really are sensitive on how we reconstruct the top, depending on which one we identify as B and which one we identify as top, or which jets are coming from B and top. So if we go to substructure techniques, where essentially we are taking a large radius jet which contains all the decay objects, then we have less combinatorial background, we have better acceptance because these things are in the central part of the detector, but of course we are essentially looking at a exponential tail of a PT distribution, so we lose cross-section. So that's the trade-off we do. Again, I don't think I need to tell this to this audience. So there are many signatures of new physics, vector-like quarks, heavy bosons, even for like standard model Higgs measurements where these techniques are useful. As an experimentalist, I'm supposed to show a picture of a detector, but I refuse to do that. So I show an event display with a semi-electronic T-bar event where you have essentially hadronic top candidate. So that's like your big fat jet. And then on the electronic side, you also get some jets. So that's essentially what you're looking at. We don't need to spend time over this at all. Right. So what we do? Deepak kind of touched on it. He talked about the filtering. But there is a wide range of grooming techniques which we use to eliminate soft radiation, underlying event pileup, and all those things. So that's essentially the first step. The second step is we need observables which separate signal from background. For example, he talked about the energy correlation functions, the end subjectiness. There are a few of those. I'll probably describe a couple. So of course, he mentioned the mass drop and the filtering, but there is a bunch of other algorithms, pruning, trimming, and soft drop. Right now, Atlas uses trimming. CMS was mostly using pruning, but they moved more to soft drop. We may be moving to soft drop in Atlas as well. And whenever I think of this, I remember this ad from Glasgow because, I mean, I was in Glasgow for a while, and this is how you clean your garden, essentially, right? And this is how you clean a jet. Right. So one slide summary of the grooming techniques. So filtering is what you mentioned. Essentially, you pick out 3 hard radiations because we expect if it's a 2-prong decay, then there may be 1 extra jet. Even if it's top, it's 3-prong decay. Pruning is essentially you throw away for all of these algorithms, you step back in the clustering history and start from the original clusters. If you have clusters which are soft or too far from the center of the jet, you assume they're uncorrelated, they came from the soft underlying event or pileup, you throw them away. And so pruning is much more aggressive compared to all of these things. Trimming, you just throw away clusters if they have less than a certain fractional energy of the original jet. So these are the 3 standard algorithms we have been using, but it's not very recent, but we are slowly moving to soft drop. One of the reasons is soft drop is analytically calculable, so you can actually do this experimentally and compare to your analytical results. In fact, I'll show some CMS results on that. So the soft drop essentially is you start with the jet, you split it in you essentially undo the last step of the clustering. If your minimum PT of the subjects, so we call the last step subjects, is greater than a certain fraction. So there are a few parameters in the algorithm, z cut and beta. If this satisfies, then you keep the jet. Otherwise, you iterate, and then at some point you get your subdrop jet. So since I'm from South Africa, I have to again show this picture. So this is what you start off with before your grooming, gardening, and then after that, maybe you see something nice. Right. All right. So since this is not an Atlas talk, although I'm in Atlas, and I don't have to show all the Atlas results, and this is a very nice result from CMS, which was shown in Boost this year. So what they did is they measured the jet mass. So this is ungroomed jet mass. So they didn't apply any of the grooming techniques. And they compared in different PT bins the jet mass against different simulations. So Pythia, Heroic++, and PowerEC plus Pythia 8. So this is the lowest PT bin they looked at, and they go all the way up to like high PT bins. So this way. Oops. Now, one thing is very interesting. We don't really see a difference between Pythia 8 and PowerEC plus Pythia 8, which kind of reinforces that these things are more sensitive by shower than the increased accuracy in the matrix elements. We also don't see a big difference between Pythia and Heroic for most of the cases. For the low PT, we have a discrepancy between data and Monte Carlo in the tails, which is probably caused by soft radiation. Who knows? But yeah, but then they also looked at the exact same variables using soft drop. So now the soft drop should cut away the soft radiation underlying event and pile up. And then actually the discrepancy is kind of larger, even for all the bins. And they also compared with the theoretical calculations of Marzani and Fry. The theoretical calculations are okay. Most cases they are okay. I think they are not perfect. Oh, they are diverging at the tails again. And generally you get less good agreement than in case of the ungroomed ones. So, so essentially the idea is we get, I think, yeah, we get better agreement here probably. Let's go back. Yeah, probably slightly better. Not, I mean, I don't see a significant difference, but that's what the CMS paper claimed. Yeah, these are the theory ones. So they are not doing very well at the tail. But again, PowerEC and PowerEC Pythia 8 are very similar, and I mean, we can live with that. I think that's my takeaway. I mean, this is very interesting. The similar measurement in Atlas is stuck at approval stage for past 2 months. Hopefully it will come out soon. Now, this was a large theme of discussion in Boost, because, of course, when you look at distributions, one of the big uses is tuning our Monte Carlos. And when we tune our Monte Carlos, we try to tune the soft part, the MPI, the hadronization, all those things. And this, I'm pretty sure Stefan Prestel said it. So it was, or you can attribute this to him. So the idea was, when we are looking at these observables, groomed or soft-drop jet mass, we are no longer very sensitive to MPI and the effects which we want to tune. But it's very hard to disentangle these things. So how do we do it? We still don't know. We had lot of discussions, and of course, the hard part and the soft part is very correlated. So that's something we need to look at. I mean, we might look at the ungroomed ones and have that should have more sensitivity to MPI, but we need to find observables which are actually sensitive to soft effects. So that's something which a lot of people are looking at. So Atlas A14 tune, which we use a lot. In fact, Andy is not here, so Andy and me did the tune. So this is number of charged particles inside a jet, and the data is actually most closely matched by, where is our A14? Yeah, and the red line, yeah, this is Heroic++ newer version. But the older PTR tunes didn't describe the rate at all, and we did a much better job. But then again, there were issues because we tuned the FSR alpha S to a lower value to get this nice agreement. That was one of the things that went in there. But then that caused some friction with LEP3 jet shapes. So people are not happy. I mean, this is 3 years old. A14 actually stands for 2014. But we haven't updated the tune. So this is something, I mean, probably this audience doesn't really want to discuss, but in Leisure we discussed a lot. I mean, do we really need to retune these things? Because we mostly use PowerHEC plus VTI, but then again, for jet substructure, the showering is important. And this was the new Heroic 7 description of the same observable, and they also do very well. So that's very new. Now tagging. The next part is once you clean up your jet, and hopefully you can measure, you can model your jet very well in your simulation after tuning and everything. You want to tag your jets. There are many, many methods, taggers, techniques, variables developed over the years. I'm not going to go over those. I mean, the first one is BDRS, which you probably all know. Essentially, they looked at VH events where the lepton from the V helped them to tag the event, and then they looked at the BB bar mass and one extra radiation. Now, the important part is this was done even before the LHC started, and people thought this might work, and it didn't work. That's an important lesson, that theorists come up with things, but then when we try to implement it in the experiment, it doesn't work because we didn't have subjet B tagging at that point. So we couldn't make this work. Something similar is now being used, but it didn't work all through. HEPTopTagger is one of the algorithms people use, experiments use. CMS has their own version of CMS TopTagger, which I believe is very similar. Now, for people who are not in the loop, HEP doesn't stand for high energy physics. It stands for Heidelberg, Eugene, Paris. Right. So what they do is they are trying to find a top, essentially a top tagged fat jet. So they start with the fat jet. They apply the mass drop, then they require we at least get 3 subjects. Then they, again, kind of mash them together. They get 5 subjects, and then they form as many 3 subject combinations, triplets as possible. Whichever triplet has the mass closest to the top, and 2 of them has to have a mass close to W, then it's tagged as a top, essentially. So this is a this is actually data. So this is the distribution of mass before applying HEPTopTagger. Now after tagging them with HEPTopTagger, you can see a much sharper mass peak. One of the aspects for all these things is how you get rid of pileup, because with increasing luminosity, we have increasing pileup, and these things hurt all the jet substructure algorithms. So we always try to test robustness of the tagging variable with mu, which is average number of vertices, and the top quark mass tagged by HEPTopTagger was roughly flat, so that's good. One of the techniques I have been working with for past few years is short deconstruction. That was Spanovsky-Soper quite a few years back, but we had a long battle to get that going in Atlas, which we have now. So what is the idea? The idea is you have the shower from top quark. So let's say that's an example. So you have the top quark radiating a gluon, then you have a W which decays QQ bar, you have the B jet which decays to gluon, and then you have some associated ISR, which in principle looks different from if the fat jet's initiated by a gluon. So what we do is we construct what we call shower histories. What does it mean? That means we look at the final state. So let's say this is a final state energy deposit, and we try to see if this energy deposit or what we do is we actually form small radius subjects. So 0.2 is what we can use in Atlas. So define 0.2 subjects. So we have 1, 2, 3, 4, 5, 6 here. And we try to see if this structure can or could have come from a top quark decay. So this, and then we have a final state, and we can go back to the initial state in many different ways. So each of them essentially is called a shower history. So we can ascribe different objects to different subjects. So consistent with all the Sudakovs and all the Diglap splittings and everything, they have to make sense. So it's consistent with QCD. So for this example, we can say, okay, maybe this is W boson splitting. There is no ISR. This is a BJ, and this is top radiation. But we could have ascribed the objects differently. So this is another way of looking at it. This is another way of looking at it. And there can be hundreds of these. So and this is assuming a signal hypothesis. And we can do the same thing assuming a background hypothesis. So we essentially sum up the probability for all the shower histories to be top-like and get this variable chi as a likelihood ratio. And this is our substructure variable of interest. Whenever we do anything like that, we need to say it's modeled well by data. It is. It's robust against pileup, more or less is. It discriminates signal and background. So this is a Z prime simulation, which gives you a top against dijet. And we have reasonable discriminating power. So that's what we did. Now what I'm going to show you is the taggers we use in Atlas. So this is for W tagging. Okay, so we actually plot this thing slightly different from CMS. CMS actually does background rejection or background efficiency. We do 1 over background efficiency, or what we call background rejection. So higher you go on y-axis is better, and more right you go is higher signal efficiency. So this is W tagging. This is for a lower PT range. This is for a higher PT range of the W. Now, what you can see is these two lines. One of them is using a deep neural network. One of them is using a BDT. I'll come back to these things a bit later. They are the best taggers for W. Then this is what we used in run 1. This is essentially a combination of D2 and mass. And then if we just use D2, this is the ROC curve we get. At higher PT, we kind of get closer to the BD machine learning taggers essentially, but still those do well. Now for top tagging, we have our short deconstruction line. We tried to use short deconstruction for W tagging as well, but it doesn't really work very well because I think it is a lot of information. So 3-body decay is much more conducive to it. So the short deconstruction is here. This is again the 2-variable tagger. I believe this was tau32 plus mass. Then we have the HEPTopTagger point and the short deconstruction line, and then this is just the tau32. And once we go to higher PT, again the short deconstruction does reasonably well at the signal efficiency we normally use, 60–70%. So that's that. And I mean, I do want to mention that short deconstruction does best among the non-machine learning taggers. In fact, we are using short deconstruction in all heteronic W prime search, which should be coming out soon. I mean, soon means a matter of months in Atlas terms. Now, let me spend a couple of slides on taggers using machine learning. So in Leisure's this year, we had a big discussion on these things. Jesse Thaler famously said, deep thinking should always be deep learning. Who knows? I mean, as we just saw, the machine learning taggers are kicking our ass essentially. But we are not using those things. But anyway, let me just step back and see how we got those lines. So we used BDT, which is essentially the built-in from TMVA, and DNN using Keras framework. We did not use jet mass and PT, but used a bunch of other variables. So this is for the BDT, you can see. And what we did was we started with 1, we kept adding variables and kind of try to check when we get largest jumps in signal efficiency, and then at some point it flattens out. So the largest jumps you get using the angular correlators basically in different forms of shapes. Now, I mean, of course, ECFs are, D2 is a ratio of ECFs, so these things are correlated. But that's what we get. And then this one is for W, this one is for top. For DNN, for computational reasons, we used a set of, or a group of observables. So we divided into few groups. So 6 groups. The sixth one included everything, which of course did better, you can imagine. This is for W, this is for top. So we found different groups, said we did the same study, and the sixth, of course, was the one which was probably used. Yep. And we looked at correlation. So this is for top tagging, BDT, and you can see the calorimeter mass is very correlated with the ECF variables. The ECF variables are very correlated with D2s, and then tau T2s are very correlated with splitting scale. So there are a lot of correlations, and I mean, we assume there is linear correlations, but it doesn't have to be. So there are many reasons we don't use these in the experiments. At least Atlas doesn't use it for tagging. The primary reason is half of the collaboration still thinks these are black boxes. I put this picture. This is an airplane black box. If you never thought about it, these things are actually not black. The airline black boxes are actually orange. Anyway, so these things are called black boxes, or considered black boxes by half of the collaborators. We haven't used it. A more serious concern is there is no robust way to estimate the systematics, because when we try to tag something using any of these algorithms, we try to get some systematics. Now, mostly these come from varying the inputs. So for short deconstruction, we use subjects. We try to vary the energy scale and the mass scale of the subjects, but we can't do that when you are throwing the kitchen sink at the machine learning algorithms. And then also, I mean, a priori, we assume the correlations are linear, but they don't have to be. So that's another issue we need to understand before we use these things. So I'm kind of stepping back now and going to show you some slides from a study we did in Lejush, which I find very interesting. Yes, please. Yes, that's probably true. I mean, at some point, you kind of see it flattens out, right? Yeah. I think we looked at it internally. Mm-hmm. I mean, you can kind of see, right? Mm. Yeah. Yeah, because I think we did it because this was the first time people are doing something in Atlas, so people are excited. They just thrown yeah. Yeah, there are. Yeah. No, I agree with you. Yeah. Yeah, I mean, if we ever use this in practice, we'll probably use 3 or 4. I mean, we are not going to use 20. Yeah, I mean, that would be hard as well, but yeah, I mean, Jesse has done. Yeah, I mean, I think there is some paper by Larkowski very recently where it's the same. Yeah, one of them. Yeah. No, I agree. I mean, I think this was done because no one did this in Atlas before, so we actually threw the kitchen sink at it, but we don't have to. Right. So, all right. So this is something we did with Jesse and a lot of other people. You can see a big list of names here. So what we tried to see is if Atlas and CMS are doing the best they can. So we define, of course, the one measure of one measure of the substructure tagging techniques is how good is the signal efficiency against background rejection. But we define another criteria, which we called resilience. Essentially, if we have a ROC curve, let's say for truth level, and a ROC curve for detector with detector simulation. If the ROC curve doesn't really move, corresponding to the same cut value of the same variable, then it's very resilient. If they move, the resilience goes worse the farther they move. So that's essentially intuitive picture of the resilience we defined. Now, then we looked at what Atlas and CMS is doing and some other combinations. So this is for two-prong tagging. So Atlas is using D2 now. CMS is using N2. So these are essentially different variants of the energy correlators. Then there is tau2-1, which people have been using for a while. And then M2 is another variable. We looked at both beta 1 and 2. And then there are, of course, different grooming strategies. So we defined, we call plain as no grooming, loose as soft drop, tight as modified mass drop tracker, and trimming. So Atlas, so whenever we do a two-prong substructure, we eventually get the mass distribution. So we use a trimmed mass. Now, for calculating D2, we also use trimmed mass in the numerator and the denominator. So that's essentially this notation. And we use a radius 1 jet. So that's essentially what Atlas does. CMS uses a tight, which is the modified mass drop. But when they calculate their N2, they actually use no groomed jets, and they use a 0.8. At least that's what the CMS collaborators in the study group told us. So we tried to compare these things. And then, of course, you can define some other variants, all tight, dichroic, which is a favorite of Gregory Sois, who is your colleague, right? So Gregory really likes this. And then, of course, you can define all loose. Our signal was a WW hadronic, and the background was QCD digits. So more there is, go to the right, it's more resilient, so that's good. And more you go up, it's more performance. So that's essentially we said signal to background efficiency. Now, let's start with the PT 500 point. So black is Atlas, green is CMS. So looks like, without knowing, Atlas optimized to be more resilient, while CMS optimized to be more performant. And we didn't know that when we did it, but that's what came out of the study. But this is where we calculate the resilience using parton to particle level. So before any detector simulation, which might change the picture. And then we go to higher PT, the performance increases. But Atlas loses a bit of resilience. Now, this is a piece of art. This can probably go in an art museum. So this is where we essentially just sweep over everything. Again, it's the same plot, but the idea is if you go diagonally up, it's better. The greens are CMS again. The blacks are Atlas. So Atlas kind of lives here. Oops. CMS kind of lives here. And then if we kind of try to unpack it, this is a nominal Atlas working point. This is a nominal CMS working point. And CMS can do better if they go to this point. Atlas can do better at this point. Since I'm Atlas, I remember the recommendation they had for Atlas, which is moving to dichroic observables. CMS, I forgot what this point exactly corresponds to. And then the whole Lejeune study is supposed to, so we did parton to hadron. Essentially hadron means no MPI, and then particle level meant adding MPI. We didn't really get done with this step during Lejeune. Hopefully by the proceedings this would happen. Then my last part is kind of going into experimental limitations. So I'll go to that. So some of you might remember this plot which was essentially held as the first success of substructure, 2 TeV resonance. This was before the 750 when, I don't know, probably not few hundreds, but probably 100 or so papers came out with the 2 TeV resonance. And that was then. Now we don't really see that. As an experimentalist, we should not trust points at the edge of the distribution with large error bursts. But I mean, there is a little bit, but not enough to get people excited anymore. Now, what happened? Yeah. Yeah. I mean, 750 was, there are a lot of other things which went wrong in 750. I mean, we knew internally in Atlas, those events had 0 jets. 70% of these events have 0 jets. We tried telling these guys, I mean, this makes no sense. What is your production mechanism if you have 0 jets? They're like, no, we are not going to publish that plot. We have something, we'll just publish. So it was a huge rift inside the collaboration, and that's what we got. Yeah, I mean, one of our graduate students made that plot, n-jets in those events, and it was like a heavily picked 0 jet multiplicity. Yeah. Yeah, but Atlas was so excited to get that bump out that they refused to discuss that plot in a meeting. No. No. I mean, I don't know if Darren has a different version of the stories. No. I mean, that's my version of the 750. Anyway, so that was 2TV then, that's now. Now, what went wrong? At some point, we realized that, of course, this is at the edge of the distribution, blah, 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 but we do not really understand jet energy scale beyond 1.25 TeV. That, I mean, this is internal. That looked like a sine curve after 1.25 TeV. I mean, jet energy scale cannot look like a sine curve. So we clearly didn't understand the jet energy scale at that range where we said we have a resonance. The other thing is, I put it in the Fabiola-like fonts, just for fun. We put a cut on n tracks to identify these things. Now, as you all would agree, n track is a very IRC unsafe variable, and a lot of theorists warned us against doing it. We did it nevertheless, and then some of us actually asked them, like, why you were doing it. They were like, no, it doesn't matter. We were like, if it doesn't matter, why don't you take it off? No, we cannot take it off because then we lose our nice peak. Anyway, so that was the story. Now, Atlas has a problem because we don't use particle flow objects. So when we go to high PT, we lose angular resolution. So that's something Atlas is trying to use particle flow. People have been trying to merge clusters and tracks in many different ways. There is something called track cluster objects which came up recently. I mean, people haven't used it in any of these searches or algorithm developments. So that's something Atlas is trying to do. Use track information with cluster information to essentially get a nice picture like this. And the last thing I want to talk about is essentially what I'm working on. And so this is essentially a boosted heavy neutrino, where you have heavy neutrino decaying via excited W to essentially a dijet and a lepton. Now for muon, this is straightforward. For electron, it's not, because in Atlas, we cluster electrons part of a jet. So in principle, if you can build a fat jet containing all three, the fat jet should act as a proxy for the electron. At least that's the idea. And then we realized, I mean, this is kind of giving you guys an idea, since most of you are theorists, things which appear very simple are not. At some point, people told us, you cannot do this because of electron reconstruction. So of course, when you reconstruct electrons, there are some requirements on isolation, Shaw shape, and blah, blah, blah. And we are like, fine. We take a heat in signal efficiency, but we are using the loosest possible electron. Fine. But then we are not actually using the electron. We are only using the electron in the selection. We are not using the electron to reconstruct anything. So why does it matter? It matters because the scale factors are wrong, blah, blah, blah. So we are still at a stage we are trying to convince people that we can use this as a physics object, which, again, for theorists is probably straightforward. For us, is 6 months of heartbreak. Now, there are other new physics signatures with non-isolated leptons. So this is something, hopefully, if we can get going, this would be useful for other substructure-based searches as well. And then, which I haven't touched on at all, is substructure in heavy ion collisions, which is a kind of an emerging area. We can do a lot with them and understand nature of jets in that heavy, dense media, but not a lot of work has been done there. So that's my summary. So this is a plot from Salam where it shows how the jet substructure preferred increase. Since this is a workshop and I had some time on my hand, I actually tried to make a new plot. And this is from 2010. And you can kind of see the same trend continuing. The number of papers grows up. So that's good. All right. And I leave you with this. So there is apparently this workshop. I don't know how many of you know this. Someone just Skyped me this link. I would not take any names. That's why I didn't put any names, but you can look it up. And that's probably the kind of things we are trying to do here as well. But we just didn't name it like that. All right, that's all I have. Thanks. You know